Today we're going to be looking at Variational Autoencoders, or VAEs. The VAE is a type of generative model. That means simply that it's capable of generating completely synthetic examples of a particular type of thing. And this thing might be faces or chairs or whatever it is, depending on the dataset that you provide. The idea is that the model will somehow have learnt the distribution of the data and how it's able to do things such as sample from that distribution to create completely artificial examples, or even things like anomaly detection or in-painting. Now, more concretely, assuming that we have some true distribution of the data P star, we want to build some probabilistic model P, parameterized by theta, that will approximate P star as closely as possible. In other words, if we have a dataset of faces, then P of x should register a high value for images of faces and a low value for images of non-faces. Now, in statistical terms, P of x is what we call the likelihood of data x given the model parameters theta. So what we're trying to do is to adjust theta to achieve the maximum likelihood of observing the data points actually included in our dataset D. In other words, it's a case of maximum likelihood estimation. Now, this is a visual example with some one-dimensional x. So imagine we have some examples represented by the dots here, and what we want to do is maximize P of x as much as possible over the observed data points, and this means concurrently minimizing it everywhere else. Now, if we have some sufficiently complex function with parameters theta, then depending on theta, this function can look like pretty much anything. But we want to find the theta that maximizes the likelihood of the data that we actually observe. Now, given a sufficiently large data set, VAEs can do this. And in this video, I'll explain how. So to get an idea of how this works, let's take a simpler example, say circles. We want our model to learn the distribution of circles. So here, we first assume that there are some underlying factors of variation that are used to generate this particular type of thing that we call circles, and we can call them position and radius. So using just these two variables, we can account for all the variation within the domain of circles. And we'll call these underlying factors the latent variables z. They're called latent variables because we never see them. That is to say, we never directly see the position or radius of a circle, we just see the circle itself, represented by some pixels in an image. Nevertheless, we get the sense that the structure of the data is in fact captured by these latent variables, and the data representation is just their shadow. For example, if you're telling your friend how to draw one of these circles, you'd presumably specify its radius and position, rather than listing out every pixel coordinate that is filled and every pixel coordinate that is empty. Now, this intuition also lies behind why the number of latent variables is usually a lot lower than the number of data variables, which in this case is our pixels. The latent representation is, in a sense, a maximally efficient compression of the data. So in a sense, what we have here is a representation learning problem. How do we find an efficient latent representation that captures the factors of variation inherent in the data? So, now that we have some latent variable z in addition to our data variables x, and these coexist with one another, what we have is a situation where for every data point there is both a data representation and a latent representation. Furthermore, we should be able to infer the latent variables from the data variables, and conversely to generate the data variables given the latent variables, where these occur via some conditional distributions. The importance of theta here is that it ensures that, for example, we generate images of circles instead of squares or triangles, say, and conversely, that we extract the underlying features of circles during inference instead of the underlying features of anything else. So really, theta is important in capturing the dataset that we want. So essentially, what we're trying to find is a joint distribution P of z and x. Now, using the chain rule of probability, we can write this as the probability of z independent of x and the conditional probability of x given z. Now, we don't really have any prior knowledge of how z should be distributed, so in practice, we just make up some distribution as our P of z. For continuous latent variables, this is typically a multivariate unit Gaussian, as we'll see later, but in theory, it could be anything we choose. Before moving on, it's worth mentioning that given this factorization, we can see that the VAE is encouraged to map the full data distribution D to a latent distribution P of z. So if we choose a unit Gaussian as our P of z, then sampling from this unit Gaussian will produce realistic synthetic examples in data space. All we have to do now is optimize theta. But for that, we have to maximize our original target, P of x. And now this can only be found by integrating the joint probability distribution over all possible values of z. In other words, by marginalizing over z. This is why P of x can now be called the marginal likelihood of x in this context. Now remember that we want to optimize theta such that P of x is high for data points that belong in our dataset. So ideally, if we could calculate P of x given theta, we could compute the gradient of this with respect to theta, say over a batch of x, and optimize theta by gradient descent or something like that. However, there is just one slight problem, and it's that this integral here is intractable. In other words, it's infeasible to compute, both because it has no analytic solution and because it cannot be efficiently estimated. For example, if we were to use numerical integration techniques, we'd require a number of samples that increases exponentially with the number of latent variables. So we can't do this in cases where there's an appreciable number of factors of variation in the data. So how do we optimize theta? Well, the VAE works around this by realizing that we don't actually need to compute P of x itself. We just need some way of increasing it as much as we can for the examples in our dataset. And it does this within a Bayesian framework. So let's quickly recap Bayes' rule. Say we have some model and it has some parameters h, which in a sense form a hypothesis. Bayes' rule can now be used to estimate the probability of a particular hypothesis h, given some observations that we call the evidence E. So here, P of h is the probability of that specific hypothesis in the absence of any evidence. This is called the prior probability because it's the probability of h prior to us having seen any observations. P of e given h is the conditional probability of observing the evidence given that the hypothesis is true. This is called the likelihood. It's the likelihood of observing the evidence given the hypothesis. The denominator P of e is the probability of observing the evidence under all possible hypotheses. This is called the marginal likelihood because it's been marginalized over all possible hypotheses. It's also called the model evidence because it reflects the degree to which the data supports the overall model, irrespective of the parameters. Now finally, P of h given e is called the posterior probability, and this is the probability that our hypothesis is correct in light of our observations E. So if we observe some water droplets falling on our head, we might assign high probability to the hypothesis that it's raining, whereas in the absence of those observations, we may not. Now, we can adapt Bayes' rule to our situation. Now our hypothesis concerns the values of z, and the model evidence is the likelihood that our distribution parameters theta are appropriate to the data x that we observe. So ideally, we'd want to maximize the model evidence, and for this, we'd have to find some theta for which the right-hand side here is maximized. However, again, the problem is that because the marginal likelihood is intractable, the posterior is also intractable, since the marginal likelihood is required in the calculation of the posterior. Nevertheless, this simple relationship means that if we know one, then we know the other, given that the joint probability here is actually tractable. This means that we can actually shift our attention from trying to directly calculate P of x to instead trying to approximate the posterior instead. And it turns out that we can do this using the method of variational inference. Now, variational inference is essentially the process of approximating some target distribution P with an approximation Q, parameterized by phi. And if P represents a Bayesian distribution, then this is often called variational Bayes, or variational Bayesian inference. Now this Q should represent some sufficiently flexible family of distributions, such that by optimizing phi, we can push these two distributions as closely together as possible. Now before moving on, it's worth mentioning that since we are sharing the parameters phi over all our data points x, this is a form of amortized variational inference. Now in traditional variational inference, we optimize our parameters phi for every data point independently, and as you can imagine, this gets very computationally expensive, especially if we have many data points. In contrast, in amortized inference, we share the parameters across all our observations, which is far more efficient and allows us to deal with unseen examples without any re-optimization. Now, this is called amortized inference, since the term amortization generally refers to the spreading of costs, and we are essentially spreading computational cost over multiple data points. Now, one common objective used for variational inference is the Kullback-Leibler divergence, or KL divergence, from P to Q. This is defined as the expected information loss suffered when we adopt Q as our model, while the true distribution is P. Hence, it's a kind of relative information entropy that we incur by diverging from our true distribution P to the approximation Q. One important property of the KL divergence is that it can never be negative, and this is because it does not make sense for the expected information loss to be negative. If P is equal to Q, then this is just 0. So let's find the KL divergence from our target to our approximation. Now in the right-hand side, we can split the quotient in the log, and then separate out log P of x through this derivation here. Now for that specific term, we don't have an expectation sign since P of x is independent of z, so the expected value of log P of x over Q is just log P of x. Now we can immediately see that this KL divergence actually cannot be computed directly, and this is because the marginal likelihood of x is intractable, as we've already seen. However, we can begin to see how this formulation helps us deal with the intractability of P of x. So first, let's reshuffle, and we can see that the log likelihood is now the sum of the KL divergence and this extra term here. We know that the KL divergence from P to Q is non-negative, so we know that our log likelihood here, on the left-hand side, is always greater than or equal to this extra term. Hence, our term here essentially sets a lower bound on the value of the log likelihood. Since in a Bayesian context, P of x is called the model evidence, we call this term the evidence lower bound, or the ELBO. Now, for the sake of completeness, it's worth mentioning that you can also alternatively derive the ELBO using a mathematical result called Jensen's inequality. This result basically states that the expectation of a concave function is always less than or equal to that function applied on the expectation. And by concave function, we just mean any function with a line connecting any 2 points on the curve always lies below the curve. How is this useful? Well, if we take our log likelihood and express the marginal likelihood as an integral, we can then express it as this expectation value over here. Now, because the log function is concave, we can use Jensen's inequality to arrive at this result here, which, as we can see, is our evidence lower bound. So anyway, using this result, we can think of the KL divergence from P to Q as essentially the gap between the ELBO and the actual log likelihood. So in other words, a lower KL divergence increases the tightness of this bound. Now we can see from this picture that maximizing the ELBO by optimizing phi and theta will simultaneously do two things. One, it will maximize the log P of x, and two, it will minimize the KL divergence from the true posterior P to the approximation Q. In other words, both the generative model and the inference model are simultaneously optimized. All this without having to explicitly calculate P of x itself. Now the next question is, how can we maximize the ELBO of a large set of data points? Well, one natural approach would be stochastic gradient descent with respect to parameters phi and theta. Given a dataset D, we ultimately want to maximize the ELBO over all the data points in D, and an efficient way of doing this is just to sample mini batches and perform gradient descent over the parameter space, where the loss function is just the negative of the ELBO. Now the trouble is, we can easily differentiate the ELBO function with respect to theta to obtain the gradient, but it's problematic to differentiate it with respect to phi. And this is because phi itself defines the distribution under which the expectation is taken. To see why this is an issue, let's analyze the gradient. First, let's find the gradient with respect to theta. From here, we can expand the expectation into an integral over z, then bring the gradient into the integral, then we realize that the gradient of the expectation is just the expectation of the gradient. Now, expectations are easy to estimate because we could just use some simple procedure like naive Monte Carlo sampling. We just extract L number of samples from the distribution, then find the mean. Also notice that we've removed the log Q term here because it doesn't depend on theta. So this is all quite straightforward. In contrast, the gradient with respect to phi is a little tricky. To see this, we can first expand the expectation as before, then bring the gradient into the integral. But now we have to include Q within the gradient term as well, since it also depends on phi. Now from here, we can apply the product rule of differentiation, then split this into two integrals. Now it's easy to see that the first term can be expressed as an expectation over Q, therefore it can be easily estimated. However, this second term is not an expectation, and so cannot be estimated easily. And we cannot directly compute it either, since in the general case, we don't have an analytic solution to the phi gradient of Q. Now it turns out the solution here is to replace Q with an equivalent distribution that is not parameterized by phi. And to do that, we simply express z as some function g of phi, x, and a random variable eta, which is sampled from p of eta. Now the trick is to define g such that phi and x influence z deterministically, and all the stochasticity of the posterior distribution comes from this eta variable, whose distribution remains constant throughout training. We have essentially externalized the randomness by transferring it from z to eta. Now this change of random variables is called the reparameterization trick, and it allows us to efficiently estimate the gradient of the ELBO. So now, the expectation is taken not over Q, but over P of theta, which allows us to estimate it using Monte Carlo sampling, since now the gradient of the expectation is the expectation of the gradient. This whole scheme of estimating the ELBO using the reparameterization trick is called the stochastic gradient variational Bayes estimator. Now before moving on, it's worth re-expressing our ELBO here into a form that enables some further insight. So if we just shuffle around the terms here, we can express the ELBO in a way that explicitly contains a KL divergence term, this time between Q and the prior of Z. Now we can see that we can, again, estimate our first expectation term using Monte Carlo sampling. And of course, we can do that with our second expectation term as well, which represents the KL divergence. However, with some design choices, we can actually give the KL divergence an analytic form, which means we can directly calculate rather than estimate it, which is a lot more efficient. In practice, this is often ensured by setting both Q and P of Z as Gaussians. Each Gaussian is parameterized by mean mu and standard deviation sigma, with the prior commonly defined as a multivariate unit Gaussian. As for Q, the mu and sigma values are computed using some deterministic model on X, and then Z is sampled using an eta that is itself sampled from a unit Gaussian. Since the Gaussian distribution has an analytic form, we can now express the KL divergence as an analytic function of our mean and standard deviation of our Q. We start with our Gaussian probability distribution function, then simply plug that into the KL divergence formula and work out the mathematics. Using some identities, we arrive at a pretty simple function, which is commonly used to train VAEs with Gaussian posteriors and unit Gaussian priors. Hence, now we only need to estimate the log likelihood. Now that's all well and good, but our next challenge is to figure out how to efficiently estimate the log probability here for our data point x. Well, we've seen that we have to estimate the likelihood term in the loss function, and this generally entails extracting L samples from the distribution of our stochastic variable eta using Monte Carlo sampling. Now, to estimate the loss over the entire dataset, we can extract mini batches of m samples each, and average the loss over each data point in the mini batch. So here, n is just the total number of data points in the dataset. Now, as it turns out, if we make our mini batch size m big enough, then we can actually get away with just extracting one sample per data point. In other words, we set L to 1, and you only have to average over the mini batch. This is called single sample Monte Carlo estimation, and needless to say, it massively decreases computational cost. So, now that we've gotten that out of the way, how do we actually compute the log likelihood itself? Well, it all depends on the type of distribution by which you choose to model p of x given z. For example, if x is expressed in real numbers, we might wish to use a Gaussian, while if x takes a binary form, as in binarized MNIST, then we might wish to use a Bernoulli distribution. Let's look at the Gaussian case first. So here, we're assuming that the generative model outputs a mean mu and standard deviation sigma for every data variable. So if we take our Gaussian probability density, we can work through the mathematics to get this decomposed expression for the thing that we're trying to maximize. Now we can see that the second term is constant, and other than that, what we want to do to increase the overall log probability is minimize this mean squared difference between x and the mean of the distribution, and also minimize this standard deviation sigma. Now, as it turns out, there are a few difficulties faced by simultaneously optimizing mu and sigma. For example, you can get a very, very high log probability by generating some mu values that are very close to x, and then pushing sigma down to some very low value, now that your mu is close to target. This behavior can lead to numerical instability in the objective function, and it may also lower performance by encouraging the model to focus on particular data variables, rather than focusing on all variables equally. For example, by generating some pixels incredibly well while performing poorly on the rest of the image. For this reason, practitioners typically forego trying to learn sigma and simply set it to 1 for all the output data variables. This means that the first term in the expression vanishes, and we're left just trying to minimize the mean squared error between x and y mu, with y mu now being the only output of the generative model, which is now a deterministic model on z. Now let's look at the Bernoulli case. This is the probability density of a univariate Bernoulli distribution, where p is the probability that x equals to 1, and 1 minus p is the probability that x equals to 0. So it's a bit like a coin toss with a weighted coin. Now imagine that x and p are vectors of length d, so it's like we have d differently weighted coins. This is now the multivariate Bernoulli distribution, which is a product of all the individual coin tosses. Now if we take the log of that, we eventually come to this expression, where the probabilities of our coin tosses are just given by our generative model. Now this is exactly the form of the negative binary cross entropy between the output distribution given by p or y and the ground truth distribution given by x. When x equals 1, we want y to be pushed towards 1, and when x equals 0, we want it to be pushed towards 0. Hence, if we want to maximize the log probability, all we have to do is minimize this binary cross entropy. So here is a quick summary of the loss functions typically used to maximize the log likelihood for the Gaussian and Bernoulli cases. In each case, the latent input is passed through a deterministic model, and in the Bernoulli case, a binary sampling operation then takes place. Now, I think it's worth mentioning that this is just common practice at the time of releasing this video. There is some research going on trying to learn sigma for the Gaussian case, and who knows, eventually that may become the dominant paradigm. Now, before we conclude, let's stick to our Gaussian case and sketch out the operation of the overall model, where we also assume a Gaussian prior and posterior. So in this scheme, we have one deterministic model, parameterized by phi, that maps some input x to two outputs, mu and sigma. Then, some stochastic variable eta is sampled from a fixed distribution, and these are then used to sample the latent variables z. Then another deterministic model, this time parameterized by theta, maps z to some output y. Now, to ensure maximum flexibility in the deterministic models, we would ideally like to use some highly expressive and powerful class of functions, and it turns out that deep neural networks are perfectly suited for the task. Now, visualizing it this way helps us to interpret the VAE as essentially a coding device. The inference model Q can be imagined as an encoder model that reduces the data X to its latent representation Z, which amounts to a low-dimensional code of the original data. Then the generative model, or the decoder model P, attempts to reconstruct the original X given this code, and the overall model is penalized according to the reconstruction error between the input and the reconstruction, which is our mean squared error for real valued inputs. Therefore, our model is an autoencoder, a model that learns to reconstruct some input through a low-dimensional bottleneck that nevertheless captures all the important information in the input. The primary architectural difference is that instead of deterministically mapping x to z like an ordinary autoencoder, this time we sample z from a stochastic model on x that has been learned through variational inference. Hence, what we have is a variational autoencoder. The other key difference is in the use of the KL divergence loss function here, which essentially acts as a regularization term to ensure that the latent space exhibits some desirable properties. To illustrate this, let's imagine we have trained an autoencoder on some generic shapes. So we have some circles, squares, and triangles. Now, a traditional autoencoder is just encouraged to learn a low-dimensional code of the data, so it may cluster shapes in the latent space like so. Furthermore, the mapping is fully deterministic, so a point in X space is mapped to a point in Z space and vice versa. Now, looking at this, if we try to generate new data from some random point, then it will most likely generate nonsense, because the decoder model has not learned to map this particular point in latent space to an output that represents the dataset. And this is due to the fact that the latent space of an ordinary autoencoder can be to a large extent arbitrarily organized. A VAE addresses this issue by mapping a point in X space to a distribution in Z space, and by pushing each of these distributions as closely as possible to the prior of Z, which in our case is a unit Gaussian. This encourages our distributions to overlap and fill all the space close to the origin. What that means is that now, when we sample from the prior, we will always get sensible outputs. To put this in more concrete terms, our regularized latent space has been trained to exhibit two important properties. The first is continuity. That's to say, smooth transitions in latent space will correspond to smooth transitions in data space. And this is because the decoder is encouraged to reconstruct the same output regardless of which Z is sampled from the posterior during training. This means that all points in the vicinity of some reference point are encouraged to reconstruct similar-looking outputs. Hence, a point between two reference points could be expected to produce a reconstruction that looks something like a mix of the reconstructions produced by the reference points. Now, the second property is completeness. This just means that there is a complete mapping between the prior in latent space and the target distribution in data space. So, whenever we sample from the prior, we should get sensible or meaningful outputs from the decoder. Now we can use these intuitions to conceptualize the delicate balance that the VAE has to strike between the reconstruction and regularization losses. In particular, we can imagine some weighted loss, where the reconstruction term is weighted by alpha and the KL term is weighted by beta. Now, if alpha is a lot greater than beta, then too much emphasis is placed on reconstruction, and we may recover our old problem with discontinuous distributions that we had with the traditional autoencoder. On the other hand, if beta is a lot greater than alpha, then too much emphasis is placed on regularization, and every posterior is going to almost match the prior. Now, this would give our VAE almost zero reconstructive capacity, since now it would produce the same reconstructed output for every input. So in a way, we can conceptualize the posterior distributions like a star. There is some gravitational force pulling them all together, and this is the KL divergence term, but there is also some outward pressure pushing them apart, and this is the reconstruction loss term. What we want is to strike a balance between the two. However, that does not necessarily mean that alpha and beta have to be exactly the same. There is some benefit to having a beta greater than alpha, as we can see in methods such as the beta VAE. So there we have it. To summarize, the VAE is a latent variable model that is able to capture the underlying factors of variation in some dataset, and map points in data space to distributions in a well-regularized latent space. They have been used in a ton of applications, and they serve as a key milestone in the field of representation learning. Now, if you want to learn more, make sure to check out the links that I've put in the description.